Sound check. We'll start in a couple of minutes. There are some batteries here. Zainab. I think it's theirs. Okay.
Looking at this, what?
We've developed this video cube as a way to kind of make it simpler for doing the recording. So this is the webcam that is tracking him. It's a AI camera, and this is the sort of selfie stick. This is the mixer and the transmitter and receiver, and he's wearing the mic.
Okay.
Yeah.
The camera is near right now.
Yes. Okay. And the remote is working.
Here it's stuck.
Remote is working.
On the screen it's stuck.
Blank. Okay.
Okay. Yeah. I'll put it on.
There. Okay, we are on.
Yeah, we're good.
Alright, let's begin.
Thank you, Kevin.
The stream is on. Okay, cool. Hello everyone. We'll begin now. Okay, so I'll first explain what the topic is all about. Fine-tune SLM with LoRa, right? So fine-tuning, basically you have a model that you are picking and you'll have a small data set. You want to customize the responses based on what your data set is. You want to respond it in a particular manner. How many of you have used, let's say, iPhones and Galaxy phones? So you would have seen, you would have email summarization or other options, right? Now maybe behind the scenes it's the same model, but it is behaving differently. So you are writing a professional email, you'll have a professional kind of a response. Maybe you want to write, like, let's say a social media kind of a tweet, you'll have that kind of a response, right? Behind the scenes it could be the same model. Like the base model could be same, they could have certain fine tuning done on top of it. Something similar is what we will observe today, right? That's the fine tuning part. When I say SLM, has anyone heard about what SLM means before? Like what is it, sir?
It's like you have a large language model, you just customize that for your specific domain and fine tune accordingly.
Yeah, so you have large language models like, let's say, Gemini, ChatGPT, whatnot, right? Now all of them are basically subscription based. You don't get the actual model binary to work with, but like, let's say most of you have used Olama, so the models that you download from there are something you can run on your consumer machines, be it your GPU based laptops, etc. So those are small language models, like limited in size. They would have limited capabilities also, but you make that particular capability so good that you can just run it for a particular use case. That's what SLMs are good for. So maybe it is paraphrasing, it could be summarization, etc. So you just pick one particular task and make that small model good enough to work on that. You don't want it to generate images and videos and do 10 things. That is something LLMs are good at. They can be multimodal, they can do 10 things. But your SLMs you will fine tune for your particular use case only, and that's like the behavior you would also see in agentic systems. So when we say agentic AI workflows, you want to use SLMs, small SLMs doing particular tasks. Like we had monoliths before in backend systems, then we moved to microservices. The reason being, a single component, a single microservice is doing one task. Something similar, you'll have different SLMs specifically fine-tuned for particular use cases, and then you can basically build a complete agentic workflow with that, right? That's the idea here. And the last part is LoRa, which is a particular technique that we'll be using today. Why do we do that? It is under a class called PEFT, parameter efficient fine tuning. And basically what that means is you don't have to train the complete model. You take the base model, freeze the weights as is, and just train the last set of layers. And that means you can have a very small data set, you can fine tune it, create those layers, and then just have we'll see a kind of a design pattern called adapter here. So you can just switch the adapters and then you'll have different responses. That's what we'll be looking at. So the particular technique is called LoRa, which is what we'll be seeing today. And we'll actually have hands-on as well, so you'll be able to build it on yourself. You can publish your models also, so we'll see everything. Yes.
So do you want us to wait till some time for questions, or you want to ask?
Keep it interactive. You can go ahead. Yeah.
So you said SLM is smaller than LM.
Mm-hmm.
Is there a clear differentiation between where SLM ends and LLM starts in terms of maybe number of parameters or the memory requirements?
Yeah, I mean, there's no fine line as such, but again, basis the number of parameters you can kind of guess. So let's say most of the SLMs that you would work with, like let's say be it gamma version that we will be using, so it would be a very small version, but again there are different variants also available in that. So once you go to Olama, you can see, for example, GPT OSS, there are two variants available, 20 billion and 120 billion. Now maybe you could say 20 billion is a small language model and 120 billion is large language model. Somebody who has a better hardware would say 120 billion is also SLM for me, right? But I mean, it's relative, but in the sense, like LLMs are in trillions of parameters. They would not even fit in your single GPU machine. Like it needs distributed training, you need to train it for months and years, and then you will get some result. SLMs are generally more better and efficient in that sense, like you can actually fit it into a single GPU if you have enough memory, etc., right? So those are some of the things, but like maybe something below 300-400 billion I would say is a SLM. Maybe if it is like, let's say 120 billion, it's very high to run in our machines. Like you actually need that amount of GB of memory also, right? But still relatively compared to LLMs, they are under the small category itself. But it's not more about parameters, but more about how do you really apply it. So we'll see basically LLMs versus SLMs. We'll have that comparison. Okay. Just want to also check, like, any of you have already done the prerequisites, like creating the Olama account and Hugging Face account? Cool. So, all right. Uh, yeah, a bit about me again. So, currently I am with G Hotstar working as a staff engineer into data AI side of things. Previous to this, I was with SAP, Walmart, Intuit, and yeah, close to 10 years of experience. That's mostly about me. Now coming to this topic, right? Like why not choose LLM? So you have a generalist model which can actually work on different domains, and but it also gets confusing. So if we look at some research papers recently, what you would observe is, like, the more bigger your prompt is. So there was this context engineering, prompt engineering taking buzzwords for quite some time now. Eventually what has happened is people have developed really good prompts. They have developed good systems to design prompts, like what is really important, constraints, guardrails, etc. But that becomes overwhelming even for LLM models. The reason being, how big your prompt is, it does not follow it thoroughly. So if you are really reaching those limits, like you are maybe within the limits also, let's say you have 1024 token size or context size. Let's say you are at half the way, right? You are maybe at 512 or something. Still, what you would also observe from research, it has been seen, like if something is there on top of your prompt, that is followed well compared to something which is towards the end. Like the bigger the context grows, your models do not really follow them. So you cannot just feed everything into a single prompt and then ask the models to work on top of it. Plus, you would have back and forth conversations, be it agentic systems or general chat conversations, right? So when you are having those back and forth, it's like every time you are sending a system prompt, so you are having that much of context already lost. And the way context is calculated is, you will have your prompts which you are sending, you'll have the inputs, your actual input that you want some task to be done, plus your output. The overall thing becomes your context, right? Now, that way, if you have a very big prompt and you want it to, like, let's say, do legal things, healthcare, etc., like a single model doing everything, so you'll have to specify those many inputs, constraints, what kind of output format you want, what the model should do, what it should not do, etc., right? So it becomes overwhelming over time. That is what has been observed, and you would see hallucinations coming out. The way to avoid it is, maybe again using the same LLM, you distribute it into different chunks. Like you'll have, specifically for healthcare, you'll have a separate prompt, you just do that work, then you have another prompt, so on, right? But there's no proper orchestration that you can build that way. You depend on a single model, and again there are limitations with different models also. So like, let's say GPT would be good with something, but there is Claude which is good with another thing. Now if you just have a single LLM doing everything, you are kind of dependent on pros and cons of that particular model, how it was trained on what data sets, etc. So there are many limitations that come in here, and the simplest way to avoid here is, like, you should have learnings from all different models, or basically trained on different data sets, which is something you can get if you are using mixture of models, right? Behind the scenes also they would have better. Okay, so now again there is something called mixture of experts, which behind the scenes models also use. So let's say you are giving a prompt to, let's say, generate an image. Now generate an image would, for you it's a single interface, you would say it's a chat GPT Gemini interface, but behind the scenes it would reroute to a particular model. It's not a same model which is responding to you, right? So that's called mixture of experts. You have different experts, and there's a orchestration layer which basically takes your input, figures out what it needs to do, and accordingly would reroute to a particular model which is good at it. So it could be code generation, it would go to, let's say, a codex model. If it is image generation, it would go maybe to a diffusion model or whatever they have for image generation, right? That way behind the scenes it routes, but for you again it's the same class of models, like the GPT OSS or whatever it is. Now what I was also talking about is this problem. You have, higher the complexity you go, like your task complexity increases, you need more reasoning. So anyone of you have heard about chain of thought? There's a technique called chain of thought. So basically you would also see that in your chat GPT or some Gemini prompts, right? You would see thinking steps, etc. So when you are asking a complex question, again mixture of experts applies there. You could directly get a response if it's a simple problem, but if you're asking a complex problem, maybe there is some reasoning involved, there would be thinking steps added. Now that is rerouted from the models behind the scenes. But when we say thinking steps, it's basically chain of thought, which is a popular technique which is applied. So it's like in your prompt also you can say, let's think step by step. That's a way to invoke chain of thought, right? What that means is, if I'm asking a mathematical problem, let's say Hari had 10 balls, he gave 5 to XYZ, like those kind of problems. So models are not good with answering those questions, any model even today. The reason is all of them are probabilistic, and what you're asking is a deterministic question. So how do you move from probabilistic to getting a deterministic output? Is basically you want it to approach the problem in a step-by-step manner. So you would say, because this was my problem, you break it down into steps, like the way you explain to somebody learning that subject. You break it down and then explain how the answer was arrived. And then you say, okay, this was an example problem, like it's a few short prompting that you do. And then you say, approach my question in this similar manner. So that is chain of thought, a simple example. But when you do that, your reasoning increases, number of tokens increases, there would be more back and forth. Let's say the model gives you an answer, but then that is not right. So there has to be some self-reflection loop also. The model also validates if the answer is right. If it is wrong, then it would again not give you the answer directly. It would recalculate. Once again validation happens, and then it would give the answer to the user. So as the complexity increases, your reasoning increases, your cost increases because your tokens are increasing. There's a lot of latency also coming automatically. So that's where you have this single problem of LLM not being able to handle everything. The idea is you have to break down the problem and then let the models approach it. If you do not do that, then basically again the same problem, like you would have some brittleness in your system, overall system, because there could be logical loops that you have missed out. There could be different guardrails or constraints which the model is not following, or basically your answer itself is wrong, or it is hallucinating. So those kind of problems can arise, and how do we solve it? Basically using SLMs. So it's not that SLMs are good at answering those things, but you make it like the expert in a particular domain, right? So, and then you will have certain guardrails also added, so you are able to overcome those problems that we spoke about. Now generally, what are the problems? The hallucination problems and etc. So we basically distributed into 3 categories. First one being domain mismatch. So let's say I have a particular case which is a legal case. Now the legal field demands that you should have clauses etc., a way to reference like from where a particular clause was referred. Healthcare would have different constraints again. You do not want to share healthcare data. You would have PII information etc., but you still want to get some analysis done. And again, different fields would have their own set of constraints that your LLM model may not be able to fit. So for example, you are into finance domain, you cannot just upload financial reports etc., because models could get trained on it. It's sensitive information which you do not want to share. Same goes with healthcare. In legal case, it is you need proper proof of any response. Like in legal cases, you need those clauses etc., so you need some references. So the citations could also be hallucinated by LLMs, by the way. How do you overcome those? So you build some techniques, like let's say there is chain of thought which you can do, but again the important point is you don't want to upload everything, or basically not want to share the data also with these models. So you could build something like a RAG system. Now again, there are limitations that RAG brings in, like how much of the data can you upload. It's again going into the prompt. So you have to first identify the relevant information, feed it to the model in prompt, and then get the responses. So there are different nuances that come in here, which is on the domain side. Next, you have static knowledge constraint. So this is not that big of a problem now, like because you have tools, MCPs, other ways, so that your models can actually connect to the internet or get real-time information. But some time back, when we did not have these kind of tools or connectors to connect to the world, you had this problem where, let's say you are asking who is the president of US, the model would say maybe a older name because it was trained on that data set. Now because you can connect to the internet, it can actually do a Google search and get the right answer. But real-time information was a problem always. And now also real-time information is available for public data, not for data that you would hold. So for example, you want to automate, you want to build your financial agent who can take actions on your behalf. Now, unless it knows how much bank balance you have, it cannot respond, right? So how much bank balance do you have? For that, the agent has to connect to your banking system, or like have some way to figure out what your current balance is, and then it can take some analysis and then figure out, okay, you should invest in XYZ or whatnot. So for that to happen, you need to maybe give it some access to your SMS, emails, or some banking way, right? And you do not want to make it public again, like you do not want to expose this information to some external vendors. So again, a place where SLMs can fit in, like your models would run locally, no data is uploaded. So it's a way, it's a win-win way where you can actually build your agentic system but not also upload the data, and because you would fine tune it for your use case, it works for your scenario, right? And one last point, again, security is also something which I have not considered here, but the other part being deployment, what we were discussing. Like tomorrow, even if let's say your latest GPT-5 model weights are available, you cannot really deploy it. Like it's unreasonable to deploy that trillion billion models to some server, because there would be cost constraints. How do you run it, distributed training, inferencing, etc. There are many constraints. But having a smaller model, it basically can run in your consumer hardware like our laptop machines, or simply run it on cloud as well. So there are possibilities where you can bring practicality to these models and bring your systems in practice. Now I think this is very important. If anyone has any questions, please do ask. All good? Okay, so yeah, now comparing LLMs and SLMs, right? One is of course size, but like how do you really go beyond size? So you have, okay, so one is massive scale, other is basically built using something called knowledge transfer. So now let's say I'll take example of Google Gemini, which is like a LLM model. They have subscription based, of course you do not have the model weights, but using the same Gemini model, you have something called Gamma, which are their SLM models. Now how are these models really created, or call it GPT OSs also, how are they really trained? So you take the LLM model and then you do knowledge distillation, or basically knowledge transfer, create the smaller variant. And the way you do it is like something we had in deep learning days also. So you have a bigger model and then you are trying to do knowledge distillation, run it on a particular data set, do training, so that your smaller models can also behave very similar to how your bigger model is doing. So you create smaller variants out of your bigger ones and try to have good validation scores, etc. And once it is ready, like it's your model available. So you have foundation models available in SLM, done using knowledge transfer from the bigger LLM models. And yeah, so basically this is like a deep architecture in the sense like you have trillions of parameters, and here it could be millions or billions depending on what kind of sizes they are bringing up with. That also means you have accuracy loss and other metrics that you're kind of measuring. There would be some hit that you take here, because of course the size is small, but still comparably good when you really look at that magnitude. Okay, this is important. So your LLMs are more of a generalist. We were talking about generalist and the problems there, right? But they are more generalist or versatile in the sense they can do 10 things. You do not want that to happen with your SLMs. You want it to do only one thing, but do that well. So you get foundation models available. Now maybe if the data sets they were using is already having that kind of a use case that you are looking at. So classic examples would be, let's say, code generation. Now they would for sure go through code generation also, and mostly it would be Java, Python, those kind of languages, because most of the data that we have available today is that kind of languages. But probably you want to do COBOL code generation or some particular use case which they would have limited samples they would have trained on. So what you can do in that case, you can take that model, fine tune it for your use case. But if you find that metrics are good enough with your SLMs, which is generally available, you don't have to really do fine tuning always also. It's more about like, does it work for your use case or not? So once you have some comparisons done, then you can figure out, do you need more fine tuning, or is the foundation model good enough? And yeah, so that was the precision focus part, and this is more resource intensive. Of course, like you are mostly using subscription based, so you do not really see how much of compute is needed or what kind of hardware was running behind the scenes. But here you will be using it for your own use cases and running it on your devices, so you'll have a better picture. Generally, the billions of parameters that you see translates into number of GBs in your RAM. So you should have that much of roughly that much of GBs in your RAM, so you can load the model and then do inferencing. Depending on how fast your machines are, you would have different flop operations that you can perform. So your latency could vary, but the idea is to load the model. You need that much of GB, translating from billions, and yeah, that would be the resource part. Now this is more privacy focused. Everything is on your device, so there's nothing getting uploaded. So that's the good part here. And agentic in the sense, I like I have a SLM which is just 270 million parameters, so 250 MB 300 MB का around वो लेता है. Now maybe that does not work for your use case. अभी जैसे simple, if I want to write an email, 270 million is good enough. Like there would be even smaller variants, like the models which are running on your phones. So let's say Galaxy AI, when they kind of sell that feature, you can paraphrase or summarize, those are running in your local machines, right? You'll have a switch to basically turn on internet access or not. So if you're turning on internet access, you are going to the LLM model, otherwise it runs in your own device. Now running something on your own device is like again a resource constrained environment, so you have to have a model which is fine tuned for that use case. But yeah, basically I have seen smaller models up to 100 MB also, like 100 million parameters, which works for your particular use case. So text based are very good, like summarization, paraphrasing, writing a email format into, like, let's say a social format. Those kind of things can work. If you are asking for it to do code completion, maybe you want to look at somewhere around 200 to 500 million parameter model, and you have those code completion happening in VS Code IntelliJ, right? That would be in this range, like 200 million, 500 million. When you are asking a model to write a complete code, you just say ki create me a website, then code completion would not work. That time you are looking at a bigger model, bigger in the sense maybe a few billion parameters, like let's say 10 billion, 15 billion is a good enough range. So depending on how complex your task is, you'll have to choose a model that way. But yeah, basically code completions you can do with a 270 million model which we have of Gamma. You can fine tune it, or you also have a code version of it, code Gamma they call it. So you can just download it and connect to your VS Code IntelliJ and run it, so you can have a local code completion model for yourself. Okay, yeah, so here it's more about, you do not have that much of performance with SLMs, because again you could have much better performance with LLMs, but here you are looking for domain expertise for your use case, security, privacy. So there are different use cases you apply each of them, right? Summarizing everything again. So SLMs, you would want to have multiple SLMs, right? LLMs, you can have just single model ruling them all kind of a scenario. Parameter sizes are again different. This definition has changed over time. Earlier it was like 10 billion was, less than 10 billion was like, let's say, a small language model, but now you are having bigger models also. We are having better hardware, so again we classify them as small itself. Yeah, focus is general purpose, but here it is more about specific domain and fitting. Overall your system would have different areas to cover. So what you would do is, like similar to microservices architecture, you will have different small language models combined to do your exclusive versatile task, but you'll have specific precision based models for particular use cases. And yeah, as we discussed, something you can run on your own machine, so that would be SLMs, and this is more about privacy, speed, return on investment, running it on your own devices. Okay, so now we see, like, let's say you have downloaded a model for your use cases, you have try to do validation, and you are getting, like, let's say 60%, for example. You want to make 60, 80. So how can you do that? What are the different ways? Maybe before we go there, anyone wants to, like, you have a model, let's say Olama, all of you have tried, you downloaded a model for your use case, you don't see that good of a result, you want to improve it. What are the options you have? So one would be prompt engineering. Anyone would be able to do that. It's more back and forth, that's why I am putting cost as moderate. Back and forth in this, you don't get good results right away, right? Plus, let's say there would be a model update tomorrow, like today it is gamma 3, tomorrow you do gamma 4. Maybe some things don't work with your prompt that you have given. So again, you have to reiterate. So if there are changes in the model, underlying backend, something is changing, then you have different results. So prompt engineering may not be the most cost efficient in that sense. Parametric, again I'm saying full. So you are doing a complete model training. You can do that as well. So you download a model, you have the model weights, and you have your own data set. So you can basically run through the full training. Every layer in the model gets trained, and that would be the highest cost also in terms of not just time but also like your dollar wise. Semi-parametric is again something like RAG architectures or connecting tools and MCPs. So you're giving real-time data so that it can have better results. So the question like I asked, like let's say how much bank balance do you have, if that is like the ground to do some analysis and do investments for you. If the earlier model did not have that information, you can connect it to your banking systems via tools, etc. So further results are also better. Or you can have simple RAG architectures giving access to internet so that it can figure out some details, like maybe what is the stock price today, etc. So you will have better analysis with your agents. That is semi-parametric. In the sense you are not touching the model weights, etc. You are having more better prompts designed through real-time information getting fed. That's semi-parametric. And something what we will be looking today is parametric efficient training. PEFT is the model technique that we call it. Why this is less cost intensive is because you train it once and then you're able to reuse it across. It's also reusable in the sense you keep the model same, like the base model you've downloaded, you keep it same, and then you have training done, you create different adapters, we call it. You can just swap the adapters for your use cases, right? The base model is left untouched. You create separate model weights or adapters, and then you are able to swap it. So that is what brings reusability here. Tomorrow model changes, you can just swap the model, but your adapters are trained, you can directly use it. Given that other things match, like the dimensions, etc., the embedding vector size. So if those things are fine, you can just reuse it. That would be the most efficient way. Now let's understand what this really means. So this is the technique, LoRA, low rank adaptation, and I'll try to explain. Let's say you have the base model. Let's say this is your gamma model, GPT OSS model. Now what we basically do is we train on our dataset and you create this LoRA adapter, right? If you change your dataset, you'll have a different adapter. So you can save the adapters, right? Your base model remains as is. This is something you've downloaded from the internet. And when I want to do inferencing on my use case, I would not use the base model. I would basically merge with adapter, create a merged model. This would give me the results that I'm looking at. Just using base model would give me a bad accuracy, bad F1 score, whatever you are trying to measure. But when I do this merging and I have this merged model, on this when I evaluate, I have much better results. Because this is where your actual training happened. You are creating an adapter, right? Tomorrow, as I was mentioning, base model gets updated. You can just swap the base model, you have the adapter, you connect with it, merge and work on it. Now again, coming back to agentic workflows. So let's say you have a use case where you want to do SQL generation, a simple example. Then you also want to do validation on top of it, and then finally actually run the SQL command. So you have, let's say, three parts, right? Like one is the planner who generates your query, then you have a validator, and then you have your actual query execution kind of agent. Now what I can do is, for query generation, I created this adapter. This adapter becomes very good at generating the SQL queries from natural text. Next one is validator. That validator would look for opening braces, semicolons, etc. So that adapter becomes good for that validation part. And for running, maybe it knows the different dialects I am running in, and it can run accordingly. So I have different adapters created for different use cases. I can keep the base model same. So again, you are not downloading 3 different models, etc. You're just having this small adapter that gets swapped. So you download base model once, reuse it across all your agents, if that works for you. Maybe there could be scenarios where you want to use a different base model. In some cases you want to use GPT OSS, maybe that is good in code generation. For others you can use gamma variants if it is just text summarization, etc. So you can have that flexibility, right? The only thing is you have your adapters for your use cases. All right. This yeah.
So basically मैंने एक प्रोजेक्ट में शीशा का प्रोजेक्ट है
Mm-hmm.
जहाँ भी हम अभी क्लाउड वगैरह यूज़ करते हैं तो कुछ तो वो कुछ देर के बाद में आंसर देना लगता है इन पाइथन.
Mm-hmm.
सो अगर मैं मेरे कोड बेस पे ही अगर किसी पेज मॉडल को ट्रेन करता हूँ तो वो क्या मेरे कोड बेस को और अच्छे से काम करेगा उसको.
Right. यही exactly problem I was telling before. So let's say most of the data sets that you have would be Python based, Java based, C++ based. अभी आपका यूज़ केस है C# में और let's say COBOL में मेरे को करना है, which is not very common, right? These models are not like the base models that you are getting from the vendors. They are not trained on that particular use case. Tomorrow you design your own language, let's say you have created your own programming language. How do you make sure कि your model is giving you in that syntax, in that language? So for that you will use your own data set, आप adapter बनाओ, and this adapter is specifically fine-tuned for your own language or COBOL or C# it is. And once you use this merged model, it will give you results in your language only, not like default to Python, etc., because that is what it was trained on. So it defaults there, right? And it may also happen after a lot of conversation back and forth. Initially नहीं होगा, it happens after a lot of back and forth, because that's what I was talking about. When the complexity increases, it does hallucinate, or basically it would default back to what it knows, right? हाँ आपको.
So you said in this architecture, the middle part of it, base model and LoRa adapter are disconnected. Right? They're joined using only defined interfaces.
Right now, हाँ.
Then we change the base model.
Yes, yes.
anytime.
So अभी आपने जैसे Olama से you downloaded something, you have used it. That's your base model. What your company or vendor is already giving you, which is available in the Olama model sub. Now we take that base model, we do the training on our data set. You create this adapter. Right now both of them are disconnected. There are some libraries that allow you to do also hot swapping. मतलब आपका model run हो रहा है, आप वहीं पे swap कर सकते हो adapter. So like how you have Olama, similarly you have VLLM. VLLM में it's a very recent feature where you can swap the adapter at the runtime. It's still like a development area, but right now what we have to do is you have base model adapters, you have both of them are separate.
The interfaces are standardized. You can
Yeah,
replace anything.
like basically both of them are binary files, right? आप उसको मेमोरी में लोड करोगे, and let's say your Hugging Face transformer या जो भी आप library use कर रहे हो, they should be able to interpret what this means. So right now both of them are separate files. Now to actually have a model object, you basically merge them, and this becomes your again a artifact which you would be loading. So right now the different libraries, what they do, they say कि give me the base model का path, give me adapter का path. You give both the path, it would read and create this merged model.
Okay.
Now some frameworks are coming up with way that you can swap the adapter at runtime. So when you say कि मेरे को email summarize करके दो, you will use email वाला adapter. Now you say I want a social media tweet I want to do. Like I want to, let's say you are a content publisher, you want to write a email subscription you want to do to your subscribers, you want to write an email post, and you also want to do it on LinkedIn, Twitter, etc. So you can just swap the adapters at runtime. Otherwise the conventional way is you will give the base model, you will give this model would be merged in memory, and then you will be able to get the inference. Next time you want to do it again, so you can recreate the model ka artifact by giving your base paths.
Yes, thank you. I have a more detailed question actually. Maybe the answer is in the upcoming slides.
You can ask, not a problem.
So what I understand from a model is that it's a layer of weights and biases. Right?
Yeah.
The input passes through different layers.
Hmm.
And there has to be a compatibility between, say you said that we will retrain some of the layers of the original model, base model. Right? We'll adjust the weights and biases. Whatever is there in
Yeah.
the model.
Yeah.
That's the whole thing.
Yeah.
Now my question is whether the LoRa adapter will also be something similar but at a smaller scale, maybe less number of weights, less number of
Right.
How will you, if the layer you are training has say 20 neurons, LoRa adapter has to be adaptive to those 20 neurons, right? Or it can happen that LoRa adapter starts with only 15 and 5 neurons are
Yeah.
coming in from the base model.
Very good point. I'll show this in the next slide.
Yeah, that's what I said.
ठीक है. So alright, I'll explain the animation, but this is your base model that you have downloaded. Okay? Now it's basically a matrix at the end, like you have layers and those many depths. So you'll have layer and number of neurons, etc. Right? So that's your pre-trained weight matrix that you have downloaded from wherever. Now what we do is, when we say low rank adaptation or the LoRA technique, you are basically creating A and B matrix, two matrices. And what happens is, simply if you run your prompt through this model which was downloaded, this would be like your final layer, the blue layer that we saw, and that's your output. Now what we want to do is, we want to customize the output. So we train A and B matrices. Let's say these are adjusted weights after our training. So now this also gives you a layer, and when you concatenate both the layers, this is your merged model, let's say, right? This is the final layer. This should be matching to what you want. The way we do training is, you load this, you create A and B randomly, you give some integers, and then you try to adjust the weights here. You don't touch this, right? What you do is, the final output after this, you get this yellow wala final layer. You merge both of them, that's your projection layer, and this output is what you are trying to do validation on. So the back propagation or whatever happens on A and B, right? Now if you connect back what I said, you have a base model which is untouched, you train a adapter, and you are trying to match your output. That's the fine tuning happening here, right? Now why the name low rank? Because first of all, why did we do A and B? So let's say I had 9 by 9 ka output, just as an example. So, or maybe let's do 9 by 9, right? So that's 81. So I could directly have a 9 into 9 matrix, but if I try to decompose it into two smaller matrix, I would have, let's say, smaller number of weights overall, because I have decomposed it into two. So that's the idea behind having two matrices. Plus, you want better outputs, what you can do is increase the width of these matrices. So this R that you see, now here I have, let's say, 9 into R and R into 9. I could have that, right? Because my output is 9 into 9, that's what I want. Now I can keep R as 2. Overall parameters would be how much? 9 into 2 into 2, because I have two matrices. I can increase R to, let's say, 4. So it would be total of 2, because I have two matrices, 2 into 9 into 4. So the compression is much better here, instead of having a single matrix. That part is clear. Other is, I can adjust the rank according to how much accuracy I want. So if I am having R equal to 2 and I am having poor accuracy, let's say it was 40% something, I can increase the rank. So my weights would increase, latency would increase, but I am having better accuracy, and which is still better than training the full model, right? This is, however small this is still, like, let's say, a minimum of 200 million parameters. I'm talking a few parameters, like maybe not even thousands. So it's much faster also. That's the idea. So you have low rank, you keep the rank less, try to have it in a manageable range, and you basically train A and B matrix. You get the final layer, concatenate with your base model weights, and the concatenated one is what you do your validation on. Then you do back propagation, adjust the weights in A and B, and then move forward, right? Generally, rank is something you'll do 2 to the power scenario. Like maybe you would have rank equal to 2, 4, 8, 16, 32. That's what have shown good results as per this. Another advanced technique on this is, so this was LoRa, you also have QLoRa, so where you quantize this out. So instead of having float 16, you would say, let's say, do it on integer int 4 or something. So you can quantize it, and that becomes your QLoRa, like even faster with a small accuracy dip, accuracy or whatever metric you are measuring. Okay, this part is clear. Like this is the crux of what we will be doing in the workshop also. Cool. Yeah, so again, bringing everything together. So you had during training, you basically had your base model, you have trained A and B, you combine them. This final is what you do your training on, and this was during training. You have separate A and B and all of this, but we also merge it, right? So what happens is, this A and B, although you are looking at an overall model level, we define it at a layer level. So I would say, for which layer do I want A and B matrices? Because we don't want to train on the whole model. So I would say I am only looking at the last set of layers. I am looking at, let's say, one layer. So I would only create A and B for that one layer, or I can do it for 5 layers or 10 layers, right? So that is something you can define, create A and B matrix for those many layers, and then finally you merge with those layers. The merged weights is what you get, and the output would be something like this. Like you give an input, you directly get a single output. All of this is taken care by the merged model, like the concatenation, etc., that you define here. Like because these are simply matrices, you can add the matrices, and that becomes your merged model. Okay, now coming to the example that I have taken, we are doing that parameter efficient fine tuning, the same LoRa technique we discussed, and these are my different data sets. So I have story generation. Now story generation could be different genres. I could have something like, let's say, dialogue generation. I could have moral stories being given. There is a haiku theme. There is mystery, horror, news report, etc. So I have different data sets. Again, you don't need a lot of data samples also. What we looked at, we are looking at training A and B matrices, which is very small. So you could have very small data set, and that is also a good thing about training here, right? If you are actually doing a full training, you need maybe terabytes of data sets. But that's not the case here. Just having 100 records also gives you good results. That's what we will see. I have 100 sample sizes for each of these data sets, and we are creating different adapters for each of them, right? So when you merge the base model with, let's say, a dialogue generation adapter, you would see responses in that manner. Maybe horror would give you horror specific responses, and you'll have moral themes, life lessons getting from the moral adapter, etc. So now in the workshop you can also do something similar, create your own data set. You can have AI generate 100 samples for you, or use any of them which I would be sharing, so you can try to generate that. So yeah, let's summarize what we have seen. So we looked at why do we need to shift from giants, or basically LLMs, to a specialist model, which is your SLM. And to make it a specialist, you will basically do fine tuning if that is the case. Like let's say the example you told, C# programming, maybe the model does not generate. Over time it would go back to Python or something. So in that case you need to do fine tuning. But if I'm already looking at Python, the existing model would be good enough. So it's already a specialist for me. Then scaling down for practical utility, like not everywhere you need to use LLMs, maybe because of security, or basically you need an external subscription. Tomorrow behind the scenes they change something, you are dependent on it, your accuracy, etc. would go for a toss, because you don't know what updates are happening in the model, which is a black box for you. But here everything is under your control. You would have that binary, so you know, like, the results would be in a consistent format. And yeah, so using adaptation, you can have basically separate domain specialist for different use cases. You'll basically train different adapters, and you'll be able to bring them together. Yeah, like all 5 minutes. Okay, so and finally the modular ecosystem. So basically you have adapters, you can swap the adapters and make it work for your use case. So that's the modular ecosystem, where you can keep the base model same, or you could have different base models if you prefer to have different in your use cases. But the idea of modularity is because of the adapters, right? You can just swap the adapters and make it work. So I'll quickly show you the examples of the data sets I spoke about, and like how the responses look like, and then we'll actually do it hands-on after the break. So okay, sorry. One second. Alright, so what I've done is I had created an Android app just to keep the simulation handy. So what you see here is Alright, so this is running through my local Olama instance. Basically, these are the different models which I had created, the same adapters that you saw, right, or the datasets. So I have a news adapter, sci-fi, mystery, etc. So these are my different tags for the microfables, I call it, and it's using Gamma 3 270 million, like the smallest of the smallest which is available. Now let's see it in action. So I'm just asking it to, like, generate. Okay, 1 second. Yeah, so I simply said write a short story about squirrel who helps its friends prepare for winter, right? That's my prompt, and this is how the response looks like. Now if you actually do this with your actual Gamma model, you would have maybe 5 paragraphs or something. The dataset I had prepared was like at max 2 to 3 lines. That's why you see smaller responses, etc. So it's more personalized or more tuned to how I want it. Now this was a generic one, but let's look at the other adapters. So this is dialogue generation. So in this case, again same pattern. I connect to the dialogue model. You will see that from the tag. I'll connect to the dialogue one, and here you would see. So again, generate a short story told entirely through dialogue between detective and suspect, and you see, right, dialogues are getting generated. Is the seat taken? Only if you promise to stay, etc., etc. So it's a proper dialogue generation. Next, let's say haiku. So this creates those 3-liner haikus that we call. Right, so this is how the response of haiku adapter is, and then you have horror. This is just to show like you can how customizable it becomes once you use the modular pattern that we have because of the adapters. Right, so now assume this was not the case, what you would have to do is if the models are, so there would be, let's say, a story generation model for horror stories. You download that, you download specifically for haiku, etc., etc. So it takes your storage, it would require that much of memory because all your models should be active, etc. But that would not be the case here. Now the 270 million model, I assume, let's say it is 300-350 MB. Adapter would be some 50-100 MB at max, and once you merge it, it becomes even more compressed. So it's more efficient in that manner, and you are having reusability, right? Yeah, I think that's what I wanted to share now. We'll take a small break and do hands-on, but if there are any questions, I can take up. Okay, we'll break for 15 minutes and come back. You have paused, or how is it?
not. It did not affect me at all. Zero effect. That's what even I think.
Hi. So can I get your Wi-Fi password?
Wi-Fi password.
Yeah, to which Wi-Fi I connect? The guest
The
password,
guest.
right? Yeah, give me the password.
Okay, so you can see my Olama screen. This is on my machine, and like this is my GPU. Let's say it is actually using some part of it. It's not voice from YouTube. Yeah, either yeah. Acha, ठीक है. So so this is my local machine. There are some processes running on my GPU, but model is not loaded right now. So you can see 0.7 GB used, right? So from this dedicated GPU, I have like 6 GB RAM, 0.7 is used, and what I will do now, I have two models downloaded. One is 270 million and another is 4 billion. Both are gamma variants, right? I can show this from this as well. So you have 270 million model, which is around roughly the same size in MB, 291 MB, 300 MB you can say, and 4 billion is again 3.3 GB, right? So we can simply use like Olama run this model name. I think most of you would have already done something like this. So the model is loaded. Let's see in this tab. You can see the increase happened, and roughly 0.6 GB it took in memory, right? There is a bit of overhead also on my system because I am running it in WSL, which is like the Linux mode, etc. But what would happen is your 300 MB model should translate to around 400 MB in your RAM. Okay, so now the model is loaded. I can simply type hi, hello, whatever, and you get the response. I can ask it to generate a story. So I'm asking it to generate a story about a brave knight, and you see like this is the response I'm getting. As I was saying, this is the default model response, right? Now write a short story about a brave knight and give me this kind of a response, correct? Now this is not something I wanted. I wanted a short story. So that's where I would do fine tuning, and for the same prompt you would see like my response would be very different. So for example, you can see that I have given the same prompt but using my version of the fine-tuned model, and this is the response I get. Response is here. It starts from here till this, right? 2 to 3 lines, because my dataset was designed in a manner like I want concise, short responses compared to what, let's say, the foundation model was giving me. Now if you have an adapter which is specifically trained for comedy responses, horror responses, your results would vary, right? But the idea is you take a base model, you see that your results is you expect a different result, you go through the fine-tuning route, the LoRA route, and once you do that you should see a difference there. Now you could have your specific validation metrics to see if it is behaving good or not, and accordingly you would do the set of trainings. Alright, so this was like how do you use Olama. So you can have like the UI mode, you can do it here as well, and I can ask the same question, or you could use the terminal Olama run, and or also use the curl way. So what we will be doing is we will run everything in Google Colab. So we'll run Olama as a backend service, and then you will be able to use the APIs because it's more like a client server architecture. So we'll make a curl call, like a API request, and then you would see the responses. That's what we'll follow there. But in your local systems, if you're running, you can use the GUI, something like this, or your terminal. Okay. What else about Olama models? So now if you go to this website olama.com and just go to the models tab, you would see there are quite a few models available. Now let's say I can look at thinking models. This is more where you have chain of thought and other techniques applied, and they would not give you instant responses. They'll go through the thinking route, so they'll validate the response, etc., and there would be different techniques which would be applied. So they have already categorized it for you, like these are thinking models. They have tools capabilities, so you can connect to tools, MCP servers, etc. Model supports that. It's also a vision model, so basically you give an image as an input. You you would encode your image and then give it. Model would be able to understand. You can do image detection, segmentation, etc. Number of things you can do. Similarly, you have many more variants available, and this is how you can look at. Many people are asking me about coding models, right? So if you just search for with something like this, like just search for code, and you would see a llama variant model specifically fine-tuned for code, which already the vendor is giving you. Similarly, there is code gamma. So we looked at gamma examples right now. The model that I was using was gamma, but maybe if I want to do code generation, I would prefer to use code llama, code gamma, right? And similarly, there are many more models. So you would first want to see like if there is a base model available that you can use directly. If it is not available or it is not giving good results, then you move to fine tuning. So okay, that was about this. And other thing is, like, let's say I go to gamma, which I have chosen. There is something called 3 that we are using right now, and there is 3n also. The difference is this is architecturally a bit different. I think they have it mentioned somewhere. Okay, so this part that you see, dynamic resource usage. So basically, let's say although you are downloading a 6 billion model, actually the number of layers that would be active would be only around 4 billion. So you have lesser memory footprint, and the concept here is like you don't need all the layers to be active for a particular task. So if I'm having a vision task, specific layers which were trained for vision, or basically specifically neurons, those would get activated, and that would be only maybe 4 billion compared to actual 6 billion. The model is of 6 billion size, but not every layer needs to be activated. So this is like dynamic allocation depending on the task. So this is something many new models are coming up with, the new approach to have a bigger model, but then the memory footprint is less depending on what kind of task you are operating at. This 3n model is also multimodal in the sense it can work on image, audio, etc. The gamma 3 that we'll be looking at is also having vision capabilities, but not suitable for other multimodal tasks. So that is one difference. But yeah, basically now let's say if I go inside this, you see that the vendor, again from Google, you are having multiple variations available. You have 270 million, 1 billion, 4 billion, 12 billion. So you can choose according to your needs what works best for you. Results with 270 million and 27 billion would be very, very different, drastically different, right? Because you can imagine the number of parameters which are coming in. So let's say for your example, you want to go with 270 million story generation. Base model itself is very good. So the smallest of the smallest would work also. But you are looking at, let's say, coding task or some specific task, which let's say the base model was performing very poorly. You want to go with a higher size, accordingly choose what you want to go with, and then move forward.
What is context here?
So this context, remember our discussion, system prompt, your actual task input, etc., and the output that you'll get. The whole thing becomes your context, and how much context can your model support? That is what it says. So basically 32K. So overall size should not exceed 32K. If it exceeds, it's like a sliding window. Your earlier context would get lost. So
What words or characters?
this is in tokens.
Token. What is a token?
Yeah, 1 second. So okay, so one basic thing to understand, if I'm using, let's say, Gemini models, they would use a specific tokenizer that would not work with GPT models or llama models. They would have their own tokenizer. Every model would have their own way of converting your text, your image into embedding that model understands. So model and tokenizer, these are like, they go hand in hand, right? Gamma models and Gemini models, they share the same tokenizer. So if you tokenize everything and keep like into your rack systems, you'll be able to operate with Gemini if you're using the gamma model or tokenizer. Now what I've done is I've chosen the gamma tokenizer here, and I would say, hi, how are you? Or some random text, right? You see that this different color shading that you see, that's basically showing me that they are considered as different tokens. And this is the token ID. What that means is, when you had done your actual training, or basically Google had done their actual training, they would have a vocabulary. So I'm saying hi would map to a particular integer. Machines would not understand hi, how are you, etc. They understand in numbers, right? So they have created, let's say, a vocabulary map, a simple map, you can say, word and corresponding to a number. So hi corresponds to 2, how corresponds to 544, etc. When I say hi, how are you, if the model responds to me hi and your name, it would actually give you token number 2. So the model responds in tokens, it would give you token 2, and this 2 is again reverse mapped to your vocabulary. Now, because you would have different data sets, every model would train on different vocabulary sizes. That's why tokenizer is in pair with models. Other thing is, if I look at a newer model variant, what they want to do is compress the information as much they can into a single token. So instead of having 4 or basically 5 tokens here for this text, the newer models would try to condense this information into lesser number of tokens. So it's better for you in terms of cost or latency, etc. So that work happens on the tokenizer side, but basically 5 tokens, so you would consume that many bytes, and that adds up to your token context. If I go into, let's say, some other version, let's say GPT 3.5 would have taken would have again taken 4 tokens here, token count is 4, and maybe if I choose actually let's do this. So I'll just copy this paragraph, and you can see there are 119 tokens in 3.5, but you see the newer model that they came up with, like let's say GPT-4, the same thing would have taken, okay, it's taking same so you see the difference, right? One was taking 119 tokens, another is taking 124. So that means this DeepSeek R1 would require more tokens to represent the same amount of information. So this would vary with your models, with your tokenizer. Okay, where were we? Cool. So you decide on the model size depending on how good your results are, plus how much information you have in prompt and etc. Now if I actually wanted a big novel to come, maybe 32K would not suffice, so I would have to by default go with 4 billion at minimum to have a bigger response, right? So overall your system prompt, your input, your output, that whole thing becomes your context, and accordingly you would decide what works best for you. This is also one of the reasons when you are in that chat conversation, you would see something you told above would be missed out because it would actually lapse your context size. So it's more like a sliding window. Alright, I would want you to maybe open this link or scan. So the workshop activity would be in this GitHub repository I have posted. So the Android app which I was showing, it has that also, plus there would be a model folder. You should go into the model folder which is present, and there are 2 notebook files there. One is for training, one is for inference.
This repo is going to remain public.
Yeah, it's public. All of you have opened, so we can go to the notebook. Alright, so coming to the notebook, this is how it looks like. Here you would see this model folder. Oh, one second. Okay, cool. So this is how the GitHub repository would look like. Here you have this model folder. Inside this you have, let me open it here. So you have a training and the inference file, right? Let's go through the inference first. So let's say you trained your model and then you uploaded it on Ollama, Hugging Face, etc. So I've shown you both the approaches. One is using transformers library, which is very common across when you are working with generative AI systems. So I load the transformers library. Unsloth is a library that we are using to fasten your training process, your inference processes. It is built on top of transformers itself, right? So I'm using something called fast model and importing torch. And so basically it's like you have torch, on top of torch transformers was built, and Unsloth again does some optimizations. So there's like a third layer that we have. So what I do is I had my model uploaded in Hugging Face repository. You can also explore this if you want. And I just load this model from pre-trained. I define like this is the full size, so I'm saying false for 4-bit, 8-bit, and maximum sequence length is 2048. So I'm saying my total context size should go up to 2048 at max, because I wanted shorter responses. If I want longer responses, you'll adjust this accordingly. The model was giving me 32K. I have restricted it to 2K, right, to have a shorter response. I don't want paragraphs and novels coming out. I load it for inference, and again, because I'm using this Unsloth wrapper, if I say for inference, it would disable gradient calculation, etc., which is required for training. So this is like a bit faster way to do it. If you're doing training, you would not do for inference part. Okay, once that model is loaded, you can use the chat template which I'm using for Gamma 3. This is model specific. So this creates the format. The input should go to the model, and I'm just doing some prompt creation part over here. Once I do that, I say model.generate, and you would see this is the response I get. Now let's understand this response first. You see something called BOS, which is begin of sentence, and then you have start of turn. There are different roles. So one is a user, which is like, let's say you and me, we would be giving some input, and this input would have system prompt plus actual task that you want to do, right? And then you would have model responding to you. So that would be start of turn of the model. So basically what we give to the model is only this part: begin of sentence, start of turn, user, and your actual question. This was my end of turn, and the model responds to you with the thing that you gave plus start of turn model, and from here is the model output. So we give till here, till model, and then the model basically reads that it is its turn, and then it auto completes. This format is Gamma specific. You would see that in the docs. So if I open Gamma documentation, you would see like how do you define the system instructions, etc. So for that we are using the same concepts. So you have to define it in this manner: start of turn, user, give your user prompt. This would have your system prompt as well if there is any. So here the system prompt is reply as a pirate. So your responses would be more like how a pirate would talk, and then you would say what is the answer to life to the universe. This was my actual prompt. Model response in the pirate kind of a language, because that was your system prompt, part of the user prompt itself. This is how Gamma works. It requires your prompts to be in this format. So we are using the same format here. So we created that format using our chat template that we loaded. This Unsloth gives you by default, otherwise you'll have to do some string manipulation and do it yourself. My actual prompt was given in this format. That gets applied as a chat template. It converts it into this XML format, and you get this response. This was in Transformers world using Transformers repository. Now if I'm having Ollama, so again this installation you need to do in Colab. So install some ZSTD libraries, install curl, Ollama file, and run it as a background process. After that I'm basically doing Ollama pull, pulling the model. Here you can see that I'm running that same model, and I'm giving this prompt again: write a short story, and you get this response. I showed you the default behavior in my system. It was like a very big text. Here it is different. You can also run it in an API manner, which would be something like a curl command, right? This is the inference part, that after your model is trained you would do this Transformers or Ollama, whatever it is. Now let's come to the training part. So what you can also do parallelly is maybe download this notebook or open this in Colab, and you can run through the cells. there are some things that you have to also add. So you'll have to add your Hugging Face token if you want to publish your model. If you are just looking at fine-tuning, looking at the response in the notebook, then you don't have to do this. Otherwise, create a Hugging Face token, which all of you would have already done as a prerequisite. And yeah, so I'm just giving like the base model, that is this Gamma 3 270 million IT instruction tuned. So you looked at those format, right? Start of turn, user model, that is instruction tuned. So you are given a base model, you can fine tune it for your dataset. That's what we are doing. And the Google, let's say the vendor, is giving you a format for you to instruction tune it. That was the instruction format. So we're using that IT variant, and this would be my repo where I am basically publishing it on Hugging Face. So I've just created that as a variable. You would just need to change these things, and the rest of the things are you can just run it as is, right? Okay, so initially we are installing the libraries. So notice for Colab I'm just saying pip install unsloth. If you're doing it on your local machine, you would have specific versions to be done. Some are already pre-configured on Colab, so you'll have that variation. Other than that, yeah, loading the base model. So let me show it from Hugging Face. So I'm going to the model section and sloth and this model variant. So this is what we are taking as a base model, and you can see that you can see this model tree. So there was Google Gamma 3 270 million, that's the base model. Now Google fine-tuned a version which was tuned for instructions, so you can give your own instructions and you can fine-tune it. So they created a IT variant which is instruction tuned, right? If you just give instructions here, it would not behave as is because it doesn't understand that start of turn, end of turn, begin of sentence. So on the base model you get instruction tuned models, and on this they have created this model unsloth. So they have again done some optimizations. So this is the fine-tuned model that we are using. On top of this, you have different people working on it. They would have created their own fine-tuned versions, just like how they did from Google, or you can create different adapters. So there are 23 adapters built on top of this. One of them is mine, which I showed you what we were running. So that's how this tree is, and I think we should see it from here also. Or maybe let me show you from my models. Yeah, so you see I have 10 different variants that you see. These are all the adapters that we discussed. So one was like a base one, then for letter format, sci-fi, news. So these are different adapters, right? So something like this you would be able to also publish if you put your Hugging Face token and use your own user ID. Okay, now yeah, basically this is where you would add your access token. If you go to your user profile, here you have access tokens. Go there, create a right level of access token, and you can continue with the exercise. Okay, moving forward, so we loaded the model from pre-trained. So we loaded that model unsloth Gamma 3 270 million over here, and this is how the model looks like. Now, okay, this is another important part, what we discussed about LoRa in the presentations. This is how the model looks like, right? So you have this decoder layer. This is the last layer, set of last layers. So you have attention block and you have like a projection block in the decoder layer. So you can notice that there are 18 such decoder layers. In each decoder layer you have attention layers, which is like Q project, K project, V project, O project, right? And these are normations. So we'll skip this. But let's say I want to do the adaptation that I wanted to do. I wanted to do on the adaptation layers over here, the attention layers here, plus the projection layers, right? What is the difference between both of them? So somebody who is not aware of attention or self-attention here in transformers, I have, let's say, a big paragraph, right? And from the previous paragraph I was referring, what does this mean? Now this corresponds to what? Is it an object, is it a person, etc.? So transformers are famous because they are able to retain some context and they know what is the important part. So I have a sentence, in that sentence what I should focus more on. That's where they say attention, right? There's something called self attention, cross attention, but in simple terms, I have given you some input. In that input, what is the most important thing I need to focus on? That would be the attention part, which comes from these attention blocks. Now, because I want model to be fine-tuned, I want it to focus on some things, so I would have to tune my attention layers, right? And projection is what you get from the output, like what moves forward. So I need to update both of them. Generally, you would want to do that, or you could also, for your XYZ use case, you might see like, okay, I don't need to update the attention. Let's say it's already a code gamma model. You want to do it for code generation. It already knows the right set of attention to give. We just need to change the projection layer. So you can just add A and B matrices here, not here. Now in my use case, I want to do it for all of them, compare the results and move from there. So these 4 projection layers, I'll add A and B matrices to each of them. Similarly, I'll do for the projection layers, right? Okay. So right now I just saved the pre-trained model as is, just to have it available. And notice here I am saying get PEFT model, which is basically parameter efficient fine tuning, the technique that we are talking about. And notice here I am giving R equal to 128. Remember, we had A and B matrix and there was a rank, like how big it should be. So I gave 128, let's say a bigger size, because my model is already small. I can have a bigger matrix which works for me, or I could choose a bigger base model and have smaller rank, so I have smaller adapter. I chose a smaller base model and I have a bigger adapter to have a balance in accuracies. And then these are my target modules. So basically, when you define these target modules, this is where your A and B matrix gets added to each of these layers, right? So when you work with this kind of training, these are the two most important things you have to worry about. One is rank, how big your rank is, and another is the target modules. The first line is for projection, or basically the attention, and this is for projection, right? Cool. And yeah, the last config that you see is LOFTQ, which is for Q LoRa, which we have not done right now, but you can also do that if required. Okay, now let's see how the model changes. So again, similar model, we have again 18 decoder layers. Now notice this thing, you have Q project, you have K project, and again you have the other layers. But in the first Q project, the base layer that you see was what we had before. If you compare with the original model, you had this base layer already. We added all these layers here. So notice LoRa dropout, LoRa A, LoRa B, and embeddings for these, and magnitude vector, right? So these are all the LoRa layers that we added for Q project. The same thing would get repeated for K project. You have again the LoRa layers, and similarly for V, for O, because all of these are what my target modules mentioned, right? So for all of them, we added something like this. You see it combined here. This is what your merged model would look like, but basically this is a separate A and B matrix that we are training, as you remember from the diagram. So we are doing this training only for these layers, others we have freezed. So it would be the exact base model, we are only doing the A and B matrix training. Okay, that was attention. Similarly, you have this MLP layer, and again here I have gate project, up project, etc., and here are the A and B layers for it. Clear till here? We'll move to the next part. Let me know if there are any questions. So we added A and B matrices for all the target modules that I mentioned. Now comes the tokenizer part. So again, going back to this, because I am using Gamma, I have this kind of a format. If I am using some other model, I would have a different instruction to be given, like the format would be very different. So again, this is something Unsloth does good for us. So it has a repository of chat templates. So I'm using Unsloth chat templates, and I'm saying give me for Gamma 3. if you are using Llama tomorrow or some other model, you would just change that. And see this chat template that you see, I'll show you this on the Ollama website also. But basically, let's try to understand what is happening. It would identify begin of sentence token. This is like a Jinja template. So it's more of a template, not everything has to be defined. So begin of sentence token would come, and if you say that role is system, so then it basically sets that. Otherwise it is regular user prompt, and here you are going through the messages, alternating between user assistant. Those are the two roles it understands, right? So that is this prompt. And if I show you it here, so you see this, right? It's something similar. So basically your model is defined to understand this template. We are using the chat template that it had, so you give some input and it would be able to convert it into something similar. So here you would again see start of turn, user, start of end of turn for that, then you have start of turn model, and after that comes the assistant role. So every model comes with its own template that you can see from Ollama also. Also, by the way, sometimes the templates here are a bit incorrect, so you would have very different results. That I have seen sometimes. So you'll have to like load this, change the template and work with it. Now, because it's been quite some time that these models have been available, they are kind of fixed. But a newer model, you might face that issue where the template itself in Ollama is wrong. So you can compare it from the actual documentations, or from maybe other vendors like, let's say, Hugging Face or LM Studio, etc. You can see in that.
The job of Ollama layer is to convert your input. If you are using the Ollama prompt, is to convert that simple string which you gave as input to this particular template.
So, like, let's say you have a Java application. You need JDK to run it, JDK or JRE, right? Something similar. So your model would understand embeddings, etc. You're giving natural text or you're giving images. So Ollama is the layer where you can connect or basically interface with the models. So converting your natural language text, images, videos, etc., whatever you give, to embeddings, and then interacting with the models. That is something Ollama would take care for you, right? It could be basically mostly inferencing or anything like connecting to the model. Ollama is one layer. Ollama is just one layer. You have other things also that you can use, like VLLM and
just a replacement.
Yeah, but basically, how do you connect to the model? So that's the interface. Okay, cool. And maybe if you folks are not aware, so this quantization that you see, Q80, there are different quantizations also available. So Q80 is like the original version, you can say. There is something called Q6, Q7, and there are more. Those are like the quantized variants. So your accuracy, etc., would drop as you move to the lower variants, but even your model sizes comes down. So if Q8 is 292 MB, maybe Q4 would be 100 MB or something. So like, let's say somebody wants to run Llama 70 billion model, you do not have enough resources, you can take a lower quantized variant. At least you will be able to run it with a minimal drop. So those are some things. Okay. Also, another thing is, you notice top K, top P. These are set as default. When you are using Ollama UI or the terminal, we are using these top K, top P values. You can change that also once you are doing, let's say, the API interface. You can customize that. All of you know about top P, top K. This way you can also customize the model behavior. So let's say whenever you are interacting with the model, how does it, so when I say hi, it would not respond hello always to me. It's based on probabilities. Now what I say is, when I say top P equal to 0.95, I'm getting a probability curve from the model. The top probabilities is what I will consider. I would only consider the 5% top probabilities, rest I would cut off. That is what top P means. Top K means out of the 64 top tokens, I'll choose one of them. So it can say hello, it can say good morning, good evening, depending on which token gets picked. Otherwise it would be very deterministic if I maybe control it this way. right? So you have some hyperparameters you can tune, like let's say temperature, top K, top P. So you can do that via the API route. No, it would be different. So let's say I'll open this.
We were supposed to take another break, but we'll take it only if you guys want to. If not, we'll continue.
Sure. Yeah, so you would see it is different for each range. हाँ हाँ मतलब hyperparameter, like that's what you mean in name. हाँ, names are fixed, like this is like a standard convention now. So mostly temperature, top K, top P, this is what you use to customize your responses. So although your model remains same, this you can apply in your Gemini, GPT 5 etc. also. If it is on the API route, अगर आप chat GPT में हो, there you won't be able to customize it because they set a default behavior. Via API you can control this to have different kind of outputs. So let's say when I say temperature equal to 1, that means model can hallucinate also, it can be very creative. If I say temperature equal to 0, it would only respond on what data set it is trained on, what it is very sure of. Otherwise it would actually tell you ki I am not aware of this. But they kept it 1 here, that means this Quen 3.5 can hallucinate as well. Okay, cool. Where were we? So this was the chat template, and we basically load our dataset. Again, that dataset is available in datasets folder. You can see this is again AI generated, 100 samples have taken. So you can do it for your own dataset or like reuse what I have. The different genres we spoke about in stories, like be it moral stories, mystery, news. So you have different datasets available. I've created the 100 samples, and it is something like this. So you have an instruction, this is my user prompt and the response, right? Short responses, and this is what we will be fine tuning on. So you can create something similar, and you would notice that I just have how many 100 samples for each dataset, right? So what I'm trying to show is you have a small model plus you have a very small dataset, still you are able to customize it for your use case. You don't need like large datasets to do that. Okay. Alright, this is about the dataset conversion. This is how it looks like right now. So we have instruction response, what we saw, and I'm just assigning user role, assistant role to it. So yeah, the content part, the output was my assistant role, and the instruction is what my user role is. So write a story, this was my instruction, I'm calling this as content, and this is role user, and the next part, the response, is again this content, and this would be assistant role, right? So I've created this part as a conversation, which is what we will use to create that XML format. So I basically generate this at the end, start of turn user, the user prompt, start of turn model, and this, right? So right now we have loaded the model, we have added the A and B matrices, we have the data set. Now what we'll be doing is actually doing the training. And okay, can somebody tell, like, to the model what will I give for training? Will I give this whole thing? When the model is getting trained, will I give this whole text to it to be trained?
You give the data set, right?
Yeah, so in my dataset this is one sample, right? So when I'm actually doing the training, will the model see the whole sample as is, like this whole text?
The prompt and the response both.
Will it see both, or will it only see the prompt?
In training it has to see both, right?
It has to see both when you are doing the comparison, but when it is getting trained, I would only give it till here, right? Till the model part. Model will generate something, I'll compare with my output, right? So if I want to, let's say, do train the model to give mathematical answers, 2 plus 2 equal to 4, I will not give it 4. I would see what the model responds, then I will do back propagation, etc.
Okay.
Right? So
But in training you have to give 4 also, right?
yeah, I mean this whole thing would go, but when
The first time you have to give 2 plus 2 equal to 4, and then in the maybe test
So-
case or whatever.
so see, I give 2 plus 2, model gives me 5, so I'll say no, your answer is wrong, it should be 4, and then do the back propagation. So something similar, this is my format. Model output is from here, right? After start of turn model. So this is what goes as my input till here, and this is something I'll compare the output with, and that's how the training loop happens. So now this is the fine tuning part. SFT trainer, basically supervised fine tuning, and we'll see. Okay, so I'm just creating a trainer object. So I have created a supervised fine tuning trainer, I've given the model, I've given the tokenizer, and this is my data set, right? So it will be able to apply the tokenizer template that we just saw, that start of turn, end of turn, all of that. And right now there is no evaluation data set, or you can also create that. Since I have 100 samples, I just want to do it on the training samples only. And yeah, some default values which I have given. What we are also doing is just training for 10 epochs. One epoch is like looking at the data at once. So 100 samples, it looks it like 10 times. Each sample it is able to look at 10 times. Okay, now so using the trainer, I am looking at, let's say, the 10th record in my dataset, and notice this text is what gets sent, start of turn, user, etc, etc. This is the whole thing, and this text to the model will be seen like this. This is the embedding, right? What we saw. So this is the whole embedding. Yeah, this is what I was talking about. So train on responses only. I'm saying instruction part is for user, response part is after the model. So only till the model before that goes as input to the model, and we compare with the response basically. And we do trainer.train. Now 10 epochs which I ran, it completed in 36 seconds. This was in Google Colab. You would see something similar once you run. So basically the point is, it was a very small model, so it was able to complete faster. And model loading also I showed you, it is in few MBs depending on how many parameters it has. So accordingly you can decide if you're having good enough. I was just looking at training loss here. You would have XYZ metrics more, like it could be F1 score, it could be custom metrics that you have created, accuracy, whatever. So you see if the model works well for you. Otherwise you can increase the rank, or you can increase the base model size, or train for more epochs. So you would have different controls or knobs that you can work with. Now after this training is done, which I did for a few epochs, a few steps, I basically now move to the generation part, and this is my input which I had given, the 10th example that we saw. I am using the content, this is the output, right? So the earlier model, on base model, you would have received something else. After training on my dataset, I am able to get this kind of a response. Combining it with the user prompt, this is how it looks like. Write a story about a turtle who wins a race against a rabbit, and this is the model response after that 10 epoch training. Now maybe you are not satisfied with this, you can increase your base model size, or you can increase the number of epochs you train for. So that's customizable. But you saw that we are able to train a 270 million model, like not actually train, but basically train the A and B matrices and get good results like this within like 36 seconds or whatever the training time was. So that is something you're able to do with LoRa, like keeping the base model freezed, not touching it, training A and B matrices and getting decent results. After this, what I have is basically more about merging the model and publishing it, so you can reuse next time. Otherwise right now it is in this Colab notebook. Again you'll have to do training next time. You want to reuse it, so basically you want to save it as well. So we save the pre-trained model. This would, when you do this, right, save pre-trained, it only saves the adapter, the LoRa adapter that we created. You want to save with your base model, so base model also we saved earlier. You can merge them later as well. I can also do save pre-trained merged, so it would create the merged model and save it. And you can see all of that happening here. Okay, so this was the merge process, preparing saved tensor model, merging weights, etc. So this is the merged model, and when you are running it in transformers or basically Hugging Face, you need something like a GGUF format which it supports. So we create a safe pretrained model in GGUF format. Here it was in safe tensor format. Some frameworks, some libraries works with safe tensor, some work with GGUF. So that way that would vary depending on what kind of, is it LM Studio, is it Ollama, is it Hugging Face, etc. So again, this is a different format. We save that as well. And this is more about pushing the model, so you need that Hugging Face token that we created above. Yeah, now I think I have the inference part here as well. So same installation that we saw before. You install Ollama plus a model file gets generated. So when you save it in GGF format, a model file gets generated. Anyone has worked with Docker before? So in Docker you have that Docker file, right? And you say from so and so. Something similar this model file would have. It basically has a GGF path. And it says from GGF path, set the hyperparameters. We saw some default hyperparameters getting applied in the base model. Right, these things. So you do that in a file similar to Docker file. You have something called model file. You have those parameters applied, and then you say Ollama create. So it creates a version for you. I got this version created, and then I can use curl API to look at the output. I'm giving the similar prompt, or you can also publish it, right? So the API to interact with Ollama is very similar to Docker, like ls, ps, create using a model file. There it was Docker file. So kind of relatable, but yeah, this is the curl, and then I do the model which I created. I add it with my username, so I'm able to push it to my repository. You will be able to see it on this. So this is how basically this works. You can actually run all of this. If you do not want to push, just don't run these last set of commands. Other things you will be able to run in the notebook within maybe 5 minutes overall. So you can try this out, and yeah, if there are any questions, let me know.
So in step 14, the 14th code block,
Mm-hmm.
it is not able to find the data set. So can I change the path to just HTTPS full data?
So I think you would not have uploaded the dataset. In Colab you can also upload this JSON file. It's there in this dataset folder. Go back to this repository, and there is a datasets folder here, right? Pick any of them, give this name in the cell, like this JSON-L name. Or later what you can also do is, because it's just 100 samples, let some AI generate 100 samples for you for your use case and try that out. Maybe it could be code generation, it could be poem generation, whatever. So you can fine tune it that way. So in this 11th cell that I have from datasets, load dataset, here you would have to change the file name.
But I have to upload this file in Colab first.
Yeah. Download any one file and upload it. It should work. Okay, if there are any issues running, let me know. I can check. Any issues running, I can come and check. Cool, I'll stop it here. If there are any issues with running, I can roam around. Thank you. Nisarga, we can stop.